supposed to summarize our morning session. So I think it was all about the phase diagram of QCD in the temperature, chemical potential, and quark mass plane. And we had 6 talks by Maria, Anja Bahn, Angel, Yu Sang, Christian Fischer, and Alexei, who discussed various corners of this phase diagram. I only highlighted some aspects, or one aspect of these talks. So I think it's fair to say Maria and Anja Bahn mainly focused on the chiral phase transition in the flavor sector and its relation to the O4 symmetry and chiral symmetry breaking. Angel and Yu had more weight on the question of UA1 symmetry restoration, which of course is a central topic in all of these talks. And all these 4 contributions dealt with aspects of the QCD transition at vanishing chemical potential. And then Christian Fischer moved into the finite density, finite chemical potential plane, presented some of his results on the mu dependence of the transition line, and in particular, a prediction for the location of the critical endpoint in the phase diagram. And finally, Alexei discussed properties of QCD at vanishing temperature and finite chemical potential. He put forward arguments that there is indeed a first order phase transition in this zero temperature high density case, and related consequences of these first order transitions to properties of neutron stars. So this is my very brief summary of what happened this morning. I think maybe we should start, at least for a while, by giving everybody the chance to ask additional questions to the speakers and bring up some of the topics they would like to see being discussed further. I should mention again, as Christian already said, he has to lecture now, and I guess he will come back in something like 20 minutes from now, and have all questions to Christian and the critical endpoint, maybe we should defer to a little bit later and maybe start with a discussion on the first 4 talks, or the 4 talks that deal with QCD at vanishing baryon chemical potential. So I stop sharing these slides, and maybe I can find the list of participants again. So if you want to ask questions now to some of the previous speakers, I think we simply can go ahead and ask questions, and we may have a few people talking and discussing, but if it's too much, then we have to go back to the modus of raising hands. But for now, I think anybody who wants to bring up a question should just start.
Well, maybe, okay, this is Maria. Thanks for very nice summary, Frithjof. And maybe I would like to highlight and come back as a question to one point which was raised by Angel, because that's important, but somehow we at least I personally always sweep a little bit under the rug. And it is the role indeed of the strange mass when we discuss universality in 2 and 2+1 flavors. Very often we do it on the same footing, but indeed Angel made a very interesting point that at least in the case of the role of the anomaly, this extra flavor may be the source of a difference. So I don't have any comment in this respect, but I think that's a very nice point to keep in mind. Maybe also in the spirit of the work which has been done by Ove and Francesca. I don't know whether Francesca is still around, where they were discussing the properties of the transition by changing the number of flavors. Indeed, we interpolate between 3 and 2 flavors by changing the strange quark mass. And Engel was suggesting something is happening there in the anomaly sector. I think that is a point where it would be nice to hear more discussions and opinion about. So I like to add this to the list of interesting points.
Yeah, I fully agree, Maria. Actually, I tried to ask this already, Engel, after his talk, and I think in this context, there's some wording going on which we may also a little bit discuss. So,
yeah,
when Engel, you had this slide with the chiral order parameter and pointed out the role of the strangeness in there.
Yeah.
But then you also said, of course, this role of the strangeness is visible for physical values of the quark masses. Of course, in the chiral limit, this particular term drops out. And that brings me to the point of language, which is also related to the UA1 case. When we talk about restoration of UA1, I think nobody really has in mind that there is an exact restoration of UA1. And so then one qualifies this by saying effective restoration. And the same in the flavor sector, talking about restoration at physical values of the quark masses and the role of the quark mass in that game, maybe not exactly what one wants to discuss in the chiral limit. So I think for me, the question in this context would be, do we think that in the limit of light quarks going to 0, strangeness plays still a role?
Yeah, I agree, Frithjof. I mean, the question is whether there is still a significant difference between a strict 2 flavor world and the 2+1 flavor in that limit you're commenting. I mean, where non-zero but the small light quark masses compared to a strange quark mass in the case of 2+1. So yeah, I think that would be actually interesting to see whether in your recent chiral limit, I mean the analysis of your group in the chiral limit for 2+1, you could look at some other parameter measuring really or 4 times UA1 restoration and see whether there's still, say, a residual UA1 breaking compared to the pure 2 flavor case, which is the one that other people analyze in the lattice. For us, I mean, I expect to bring about some more results soon. We are still working on it, but as I said, I mean, apart from this difference between the say kaon and kappa susceptibilities, which apparently hint to the role of strangeness, we have some. We're currently carrying out some analysis of the individual kappa and kaon separately, and those can be can provide more quantitative information. So I expect to have some results about that soon. But the hint is that actually a strangeness, or the role of the strange condensate particularly, may be playing a role here, which is of course something you can see in the pure 2 flavor simulations.
Yeah, so I think actually from that is, I asked you what is the theoretical hint for the role of strangeness other than lattice calculations. So my feeling is that maybe you at present put too much weight on the lattice results as being the final answer.
I'm saying, not at all. On the contrary, I think that there's no real final answer there. And what I'm trying to see is whether actually we should still be calling that a controversy, or rather just something that can be actually reconciled.
Yeah.
Simply from the fact that these are two different limits, and it's perfectly compatible, and one of them sees more breaking than the other in the U1 symmetry. So the thing that particular term that you were asking me about is true that it vanishes in the chiral limit, but the fact that it's proportional to both the chiral limit and the strange Quark condensate is what is actually leading us now to consider that in more detail.
Yeah. So I mean, Maria asked whether Francesca has something to say about it. So I guess the striking difference, of course, at present is that it's not, from the lattice side, it's not only a difference between 2 versus 2+1 flavor, but it's also a question of discretization schemes.
Sure.
So
if I may add, yeah, thank you. And thanks, Maria Paola, for pointing out that we are simulating also in between NF2 and NF3 with the staggered formulation that allows us to simulate non-integer number of fermions. And now this is still an open question, but in principle, one might imagine to map this non-integer number of flavors into a theory with 2+1, where the +1 has a mass that goes from infinity to 0, while we span the range between NF3 and NF2. So it would be interesting in that respect to see the role of this 2+1, to see the role of this strange quark modeled by staggered quarks with degenerate flavor content. I don't know if this is what also Maria was hinting for.
Yes, I was indeed thinking, ciao Francesca, in these directions. And now that mentioning interpolation, in fact, I think there is interesting analytic work. I may be mistaken, maybe by Thomas Frithjof and perhaps Bob Schrock, in which the interpolation, in which this sort of mapping between non-integer number of flavors and the finite quark mass is shown explicitly, also in relation with the nature of the transition. So at least this is done in the vicinity of the conformal window, so for a larger number of flavors, but probably this would carry out also to small number of flavors. So yeah, I think it's a very, especially because when we think of the Columbia plot, indeed we have always this line we draw from the corner of NF = 2, and we go down vertically towards the strange quark mass. And so we say, oh, this is the region where when it is 04, this stays 04. But yeah, indeed, there is something more subtle going on there. So I don't have anything more to say, but it's interesting to listen to this discussion.
okay. So should we talk a bit about, I mean, the question which always comes up is, of course, the UA1 restoration. In this context, Maria mentioned the nice relation by Angle on the relation between screening masses and susceptibilities. Should we talk about this a bit? I actually find it also interesting because Anja Bahn actually has a backup slide on that.
Yeah, I was going to say that. You wanted me to share that?
Yeah, that would be interesting. So for me, this trace is actually back through this paper by.
Yeah. So can you see it now?
Yeah.
Yeah. No, the thing is that actually, if of course under some assumptions, which is basically sort of a smooth temperature behavior of the ratio of screening to pole masses, which may or not be true for all channels, but apparently for the relevant channels, apparently this is something that can be not only guessed but also proved in some analysis. I remember a work by Ishii and collaborators, which actually deal with, I'm not sure in which model, but probably was NGL. But anyway, they deal with both pole and screening masses, and apparently they get that for most channels, the difference are small up to the critical temperature, and so this assumption may be all right. If that's the case, because the susceptibility is a zero momentum correlator, you will expect the scaling of the screening masses typically to behave as the inverse square root screening of the top of the susceptibilities. So this is this column here, the central column here, right? This is what Maria Paula was talking about. The third column is what will the wide identities tell you if that's the case. So if this screening versus susceptibilities is okay, then what will the wide identities which exactly relate susceptibilities Quark condensates will tell you. For that, we've been doing some checks, and apparently it's okay. These are, sorry, because these are still all data from the 2011 screening masses, but we think the same behavior is seen in the newest data. But the thing is that plotting for each channel the ratio of the screening masses with what would be expected by this scaling, they tend to be more or less overlapping up to TC for the pion, the kaon, and the kappa, and the SS bar channel, which are those shown here. These 4 channels. For each channel, you have 2 sets of points. One is the direct screening mass obtained for the lattice. The other one is the scaling of the condensates in the same lattice setup, if that equivalence were true between the screening and the topologic and the susceptibilities. The thing is that apart from the numerical agreement of this is the fact that the tendency for different channels, so the trend for the different channels is also explained in that way. For instance, for the pion, you have a stronger temperature growth, which will be dictated by for the reason that this comes inverse to the light quark condensate. If you go back to the previous slide here, you can see that, right? Whereas for the kaon, you have this strange condensate, say, contamination that makes it grow slower than the pion mass. This is this one here. For the SS bar, it's almost only strange, basically, what dominates. So it's even smaller, even softer. And then an interesting one is the kappa one, because the kappa one, this combination actually would predict a minimum, and this is actually what you see. You would see a minimum around here. So that's something that tends to give support to this idea of the scaling of screening masses, which is, of course, what you measure in the lattice with topological susceptibilities, even though they in principle are different quantities, because one comes from the screening pole, the other one from the pole mass, the other one is the screening mass, but still this could be something interesting to look at.
Now that's yes, if I may comment, indeed, that's conceptually super nice. Concerns on my side are more on technical level, because on the lattice, this susceptibility suffer from very strong ultraviolet divergences normally. So I don't know what's to make a practice. And also, I also think perhaps in general, one should also introduce wave function renormalization factors, but maybe those are finite, so it's not so important. But these divergences are really a nuisance. And that's a pity, because as you say, susceptibilities are easy quantities, so you don't have to make feeds to extract the masses, so it's very nice to handle susceptibilities. But then there is this issue, and so I want to ask also others, what do they think, especially Lattice colleagues? Does it make sense to integrate susceptibilities only up to some, introduced by hand some finite cutoff in the integration of the correlators, or this becomes to hand waving and we lose the nice properties, theoretical properties? So I absolutely agree with what Angel has presented, but I'm just not sure how to use this in practice in the lattice calculations.
Well, yeah. So maybe, yeah, I think it would be nice if Anja Bahn could show one slide, because we actually looked at this, a part of this also recently. The formulas Angel brought up to us came actually out of this paper by Rajagopal, Krishna Rajagopal and Wilczek, where they relate the critical behavior at the QCD transition to, as you also said, to the longitudinal and transverse susceptibilities. And this is
yeah, but those was for the pole mass. That was for the pole mass. For the pole mass, yes, that was more natural. I think it extended also to the screening masses. Yes. But okay, that's fine.
Right. And this is now for the screening masses. So I don't know, Anja Bahn, do you want to say something about this slide?
Yeah, so here we show the two different calculations of the pion mass. So the calculations are of course on the same ensemble, but in one set of calculations we so it's a comparison of the pion mass, and so one set is from the chiral order parameter, which is so basically what is plotted as the h over m from the perspective of scaling and order parameter, and the other set which are being calculated by Simon Dentinger, that is plotted as the termed as field symbols and termed as mass. Those are from the Mesonic correlators, and summing them these are the masses, sorry, not summing them. So these are the fits to the correlators and getting the masses. Okay, so up to certain factor, an overall factor which we expect from really from these definitions to go to the scaling side. So there may there could well be a overall factor, but the trend is completely consistent. That's what the message from this slide, I think. Yeah, if Frithjof I think wants to add something.
Well, the point, I guess you said it in between, but should be clear that the masses here are the screening masses. And
yes, that's the fit. Yeah,
and the h over m, which is written there, that is exactly the same formula Angel also wrote down for relating the pseudoscalar screening mass to the chiral condensates. So that is, of course, the subtracted chiral condensates there.
Yeah, that's it. That's the word identity. Yeah.
Yeah, that's the word identity.
So the thing that the word identity relates the susceptibility. So in principle, should be the pole mass. Now, if you assume also that the screening mass behaves in the same way, you will get that for the screening mass as well. Yeah.
But anything based on word identities, now I come back to this issue of screening masses versus pole mass. Anything related to word identities should be always true also in the symmetric phase. But then, but we know that in the symmetric phase, the pole masses and the screening masses are very different. So how do we? So which one is true then? now if I think again of this connection of the susceptibility, yeah, sorry. No.
Yeah, I would expect it only for below TC and at most around TC, but not well above it. So, yeah,
but then
you're
it's
right.
strange.
Above TC, it should be very different. Yeah.
But then
no, the thing is that there is no. The thing is, there is an assumption, and that assumption may not hold for large temperatures.
Yes, definitely. For large temperatures, this breaks down.
It breaks down. Yeah, exactly.
Yeah. So I mean, the left-hand side and the right-hand side have completely different limits in the infinite temperature limit.
But I mean, the word identity is always correct. So for the biomass, the word identity is somehow word identity. So the fact that you have a relation between
but
you need the pole.
Exactly, the word identity relates to the susceptibility, which is the pole mass.
Yeah, you're right.
You need the connection. You need the connection with the screening mass, and that's an additional assumption. Yeah.
Absolutely. Yeah. Exactly. So and the screening mass then should, but you feel that indeed the screening mass should be true also in the symmetric phase, the relation. There is.
Yeah, I mean, the word identity could be checked as well. I think that Frithjof actually and his group, they did some checking of that word identity for rather high temperatures. I mean, with the susceptibility. In one of your papers, it was checked, right? It was fine for.
Also, the temperatures in this figure are not really high; they are close to the transition.
Yeah.
And the divergency, sorry, the last point, and you're taking care of the divergency just because you are using the subtracted chiral condensate. Exactly. But how do you deal with the divergences in the point-like divergences on the correlators? I mean, the contact term in the correlators.
Yeah, of course, one doesn't need it here, but when one wants to do something with susceptibilities, we also had in mind what you said, namely leave out the contact terms at short distances and integrate the correlators starting at a certain distance. That might be an option.
But what have you done here, actually? Because you have such an excellent agreement. And how did you...
The infinite distance behavior of the correlation function that gives you the screening mass. You don't have to worry about short distance behavior of the correlators.
But when you measure the susceptibility, you say you measure the susceptibilities and so forth. But the susceptibilities are from these derivatives, are not from the integral of the correlators. No, that's a completely different story, though. Because okay. Now that's different. I understand. Thank you very much.
Yeah. We have a raised hand. Maybe we ask. Oleg wants to say something.
Thanks. I have actually a naive questions. What about the dimension of this relation? It looks like that G has a dimension 2, right? Sorry?
G,
yeah, and if you integrate it over, exactly, G has dimension 2, right?
G, okay.
And if you integrate it over D3X, it seems you have dimension -1 mass dimension, not -2. Maybe it's also some constant appears here in this relation.
No, but the integration should be overall space-time, right?
Yeah, but it is integration over 3 over. If it is over 4x, it will be so it's integration over d4x, not d3.
D4x,
right?
D4x is D4x.
I see. Yeah. Then it's okay. Sorry, thanks. Okay. So it's d4x. Thank you.
Sure.
Frithjof, can I ask another question about your other definition? This is Gergő here.
Yes, Gergő.
So for the open points, when I get it correctly. So you say that M is the subtracted condensate, but what kind of subtraction do you mean here? Zero temperature?
No, there's the same subtraction Angel had on his slide.
So this strange susceptibility
subtracted.
Okay.
Yeah, exactly. What I showed was also the subtracted condensate. Yeah.
Can you see that the definition is here?
Yes.
The first equation.
Mm-hmm. Okay, thank you. Can you go back to the plot that you just showed?
Yeah.
I'm just so puzzled by this really perfect agreement between the two definitions. Do you understand how this is so nicely on top of each other?
No, but I said there is an overall factor of this large. So we are trying to figure out how and how can we calculate this factor. This is just a overall scale matching. After that, you see this on top of. But that was done to show that the qualitative behavior is completely same.
Yeah, but I mean, so again, what is the dimensionality here? If I look at m pi squared equal to h over m, how does the dimensions add up there?
M and H both are dimensionless. Okay. So
yes.
So what you see here from the chiral calculation, which is this right hand side, that is proportional to ms something proportional to ms m pi over fk square. And that was also calculated from the mass. So I calculate the mass in lattice unit, then convert it to m pi over t, and then convert it to m pi over fk. And
but
then,
you still miss f pi, right? So this is PCAC in the end, this story. So there must be
no, not really, because that would be h times m on the right.
It's
no.
Exactly.
No. It's m divided by psi bar psi, isn't it?
Yeah.
M is psi bar psi, and H is the quark mass.
Yeah,
and so f pi should be there.
Yeah. This comment was there in the Rajagopal Vilcek paper that this may not look as the Jua relation we should expect, but in the particle physics constant, yes, there will be dimensionful f pi is there, and the relation will look a little as we know it is. So there is a comment about it. I can't remember offhand, but yeah.
So this relation written in this term is the statistical mechanics statement that the square of the inverse of the correlation length has this kind of relation with the order parameter and the breaking field. So that's, I think, that's the Vilcek Rajagopal reason. I mean, that's statistical mechanics stuff. Yeah. Then, of course, but then also that also comes back to the wave function renormalization that I was mentioning in the other context. Of course, in a particle physics setup, that's not so straightforward. I mean, you have other factors, but that's
Maria Paola, if I may add something.
Yeah, please.
I think what is highly non-trivial here is that say expected, say PCAC or low energy relation, how you call it, is maintained at finite temperature near the transition with the same scaling, and that comes from the water identity. I mean, there's no reason why this PCAC relation should be maintained at finite temperatures for all over those temperatures, because this is a low energy relation.
I think as long as you can define a pole mass, because this follows just from symmetries, then it has to be correct. Indeed,
well, that's another way to put what the water identity is saying. Yeah, I agree. Yeah, but that's for the pole mass. What the connection with the screening mass is not trivial.
Yeah, that's why I was so intrigued by I knew this for pole masses, but for screening it's very, very interesting.
Maria, just to get it right, it is not quite PCAC. PCAC says m squared f pi squared equals m times psi bar psi.
Yeah.
And here it is m divided.
The scaling, probably the scaling is the one you would expect from a PCAC. I mean, if you assume that f pi is almost constant or something like that. I mean, the scaling of finite temperature compared to zero temperature is something that. Yeah, but you're right. The relation itself is not PCAC.
Yeah. So in the Rajagopal Vilcek paper, there is a discussion how one has to think about the pion mass dependence of f pi in order to end up with the inverted relation h over psi bar psi instead of h times psi bar psi.
Yeah, but anyway, as Oleg was pointing out, probably you need other dimension. I mean, you have other quantities in general.
Yeah,
So,
sure.
Yeah. To have this in this form, that's only in a case of a very. So the fact that you can, let's say, the integral of, let me put another time, the integral of the propagator is certainly correct, that in the end has to give you this relation. But to connect the integral of the propagator with the pole mass, you need additional assumption on the dynamics. So normally there is no simple relation between the integral of the propagator and the pole mass.
Yeah, that's right. Here it is just a screening mass. We have a hand on raised by Heng Tong.
Hello, can you hear me?
Yeah.
Yes. Yeah. I just have a comment. So you're talking about what identity, where it's for screening mass or pole mass, where it's hold at low temperature or high temperature. Actually, we have checked that 200 MeV it certainly holds. There's no doubt that gonna invalid. We actually also checked it in the presence of non-zero magnetic field. It always holds. So because on LATTICE Q3 we compute the 2-point correlation functions of pairs. So does not really distinguish between the screening masses and pole masses. Just 2-point correlation functions.
Yeah.
Yeah, the space-time sum of 2-point correlation functions times Lattice Quark mass goes to carry constant.
Yeah.
That's my comment.
Maybe if I can say, I mean that's what the, I mean with respect to the, if I put something some susceptibility here, the corresponding susceptibility, then that's the real word identity. But relating the susceptibility to the mass is the non-trivial thing.
Yeah, sure. There's amplitude in front of it.
Yes, exactly. Yeah. That's what I call the wave function normalization.
The susceptibility relation is the exact relation, and that should be valid everywhere, because that's comes from the symmetry. Okay, and that's nothing but the transverse susceptibility definition in the spin model. So that is
exactly perfect.
But the non-trivial thing is how you connect to the mass, and that's where all this quote-unquote ambiguity comes. I mean,
yeah, sure, sure, yeah.
Yeah, I mean, I agree. There are all sorts of let's say residues and things that one should take into account to establish a true, I mean, an exact connection. But this is what one is assuming, that all those residues, all those dependencies, the temperature dependencies is soft compared to the other part. So yeah, I mean that I don't think there's probably any mathematical connection between them. It's just something one has to check.
There is also discussion on discretization schemes. I also have a comment on that. Maybe I can share screen a bit. Can I share a screen to show you? Okay, just 1 second. All right, can I share a screen? Okay. I think I cannot share a screen. Can you just let me share a screen?
Roman, you have to do that?
Oh, now I can do, oh, no, not yet.
Okay.
Yeah, so basically what I was trying to say is that for a staggered discretization scheme, we look into a carrier constant, Quark carrier constant at 200 MeV. And even at final lattice spacing, along the lattice spacing, we don't go to continuum limit. We said at each non-zero lattice spacing, the carrier constant will go to 0 in the carrier limit. And the reason why it goes to 0 in the carrier limit, just because the staggered fermions, it preserves a part of carrier symmetry, that is O2. In that sense, we'll say that the carrier constant goes 0 in the carrier limit.
At high temperature.
At high temperature, sure. At 200 MeV, that's what I mentioned. Right. Yeah.
Yeah, okay, let me add, that's true. And let me add that when we use the Wilson fermions at maximal twist this has a similar property. So then that's the advantage with respect to ordinary Wilson fermions, that once you have tuned to the maximal twist, you scale directly with the twisted mass. And that's also why in defining this subtracted condensate with this different order parameter, I could simply multiply without any other formality with the twisted mass, because it becomes equivalent in a sense to a staggered mass. That's an advantage for these fermions.
Okay. I think we had already a lot of discussion about the zero temperature corner of the QCD phase diagram. Since Christian is back, we may use the last 15 minutes or so to discuss a bit about the finite density section of the QCD phase diagram and address the talks by Christian and Alexei. If there are questions on that. I see a hand raised by Jan. He already raised his hand during Christian's talk, so maybe he can come up with his question now.
Okay, thank you. So I have a question about Christian's talk, and basically, well, maybe he showed on slide 13, he showed really the zero temperature, high chemical potential behavior of his approach. And what was confusing me there is that actually when he showed these two lower and upper spinodal of the phase transition, that the lower one was somewhere around 300 MeV mu Q or 900 plus something MeV in mu B. And that's basically where we expect the nuclear liquid gas transition to be, and not some deconfinement or chiral phase transition. So I wonder, is really, because he always only shows basically everything as function of chemical potential and not at density, which you also could, and then says, okay, here's the critical endpoint, and beyond that, here be dragons. The question really is, if already the phase transition at zero temperature in this approach is basically ruled out by what we know about nuclear matter and neutron stars, how in that context, how reliable can then any critical endpoint prediction be? That's kind of what I'm worried about, and I would like to hear his opinion about
this. Currently I cannot share my screen. Probably Roman, you could change my status.
Yeah, try now. So
much better. Just to make. So you were referring to that slide, right?
Yes, for example, yeah. So there's
yes.
Right?
Okay. So the point is, of course, we all believe, and this is also what we should find in this approach, that the chiral transition is a bit after the nuclear transition. Absolutely. Now, actually, this is slightly larger or in the vicinity of the nuclear transition, right? So I don't know why you think this rules out
it's not,
this result.
It's not ruled out. If you plot it as function of mu, then it's still possible that it's like after another 20 or 50 MeV, then there's another transition. I don't know.
Absolutely.
But that's why I said maybe it makes more sense to plot this whole thing as function of density, because as function of density, we have some idea up to which point nuclear matter actually works, and after which density it doesn't work anymore. That was more.
Absolutely, this is correct. And in order to do so, what I would need to do, and we have not yet done that, is to calculate the density in this framework at finite chemical potential.
But you have Chi2, right? So Chi2 is the derivative of the density. So
yeah, precisely. Then you integrate, and this is basically how you can get it. Yes, but we simply did not do that yet, right? But I'm positively convinced that what we find here is I mean, okay, let me also say this calculation here is done in a slightly simpler truncation as the one that we use to determine the SEP. So give or take, there might be 10, 20 MeV shifts in this or in that direction when you increase the precision of the truncation, right? But I definitely don't think that anything is ruled out at this stage.
Oh, I would be highly excited and super happy if you had an equation of state which actually have both constraints in there. That would be great, because then finally we could do some simulations which have these, you know, spinodals and everything. I'm just saying, in my experience, usually then it's very hard to reconvene both the nuclear density and the high chemical and the high critical endpoint. If you look at densities, if you really take it seriously, that's all I'm saying.
I fully agree. This is something we should work, and we have to work upon. I fully agree with you on that. Absolutely.
Actually, as we are on this slide, maybe I can ask just for understanding. Your calculation is always an equilibrium thermodynamics calculation, is it?
That's true, yes.
So the question, why do the spinodals play a role in this figure at all?
The spinodals are the places where we see two separate solutions in the Quark-Dyson-Stringer equation. This is how traditionally, I don't know, several years ago, let's say in the NGL model or so, these spinodals have been viewed. So they are not spinodals in the sense of thermodynamics. They are spinodals in the sense of, okay, from here to here, there is one and only one solution in our Quark-Dyson-Stringer equation, namely the one that breaks chiral-symmetry. From here to larger chemical potentials, again, there's only one and only one solution, which corresponds to restored chiral-symmetry. And in this region between the spinodals, we have both. And of course, thermodynamics decides which one is the minimum, right? Which one is chosen by physics. But since we did not do the thermodynamics in this calculation, we just show the boundaries and where we find these two solutions, and that's it.
Okay, so it's an effect of the truncation.
No. This has nothing to do with the
truncation. You don't have a convex
generic
potential.
thing. Sorry?
Somehow you lose the convexity of the potential. You have two different.
Okay. Well,
yeah.
You have to exactly. Yes, this is true. Yes. I agree. Yeah. That's correct.
I can't raise my hand. Can I ask something?
I have another question here first,
okay.
Which unfortunately is a Russian name which I cannot read. Sorry.
Nuzga Mahaljani.
Okay, thanks. Yeah. Please, can you ask? Okay, somehow we cannot hear him. Then maybe Anja Bahn, you can ask your question first.
There was a slide where you showed that shifting the TC at finite mu b, and then you recalculated the different order ratio of susceptibilities.
This one.
Yeah, exactly. Yeah. So just so was that shift by some MEV in the TC mu b, was that a constant shift, or you really chose a different line of TC mu b altogether starting from 0 mu?
No, it's actually it's a constant shift. So without shift, we're going along this line.
Mm-hmm.
And with shift, we're going along a shifted line.
Okay. So that changes also then the TPC at mu b equal to 0 then. Okay.
This is true, but because the susceptibilities are mostly flat in that region, it doesn't change the picture, right? Whereas here in this region, there's a lot of change, and therefore, if you do small changes in small shifts in MEV, the whole way the curve behaves changes. This is why the change is much more drastic here than here.
Okay.
Was that?
Yeah. Thank you.
I would also have, there's a question by Oleg first.
well, thanks. I actually would like to ask whether it's possible to get the analytic structure, say, of propagator by solving the Dyson-Schwinger equations, because this is quite sensitive to the non-perturbative structure of theory.
This is actually an active line of research. So in principle, yes, we can solve Dyson-Schwinger equations in the complex momentum plane, which means we can directly solve them also for time-like momenta and thereby explore the analytic structure. What you generically find for the Quark propagator is a pair of complex conjugate poles in the time-like region. Whether this is the end of story, or whether more complete truncations change this picture is, of course, something I cannot say. But it appears so in all truncations that we resolved so far. And this means, all truncations means from the very simplest truncation, where we just do models for the gluon and the quark-gluon vertex, up to more advanced, where we start to include the quark, the gluon and ghost propagators, up to the most advanced truncation, where we include the vertex equation for the quark-gluon vertex, for the 3-gluon vertex, for the 4-gluon vertex, for the ghost-gluon vertex. In all these truncations, the picture stays the same. The quark propagator has complex conjugate poles. So that seems to be quite robust, but okay. This is as far as what we can tell so far.
Well, I think this is quite interesting because, well, first comment is that the similar complex conjugate pole do appear for graviton propagator, to some massive correction to graviton propagator. Second comment is that somehow it's quite often happens that the analytic structure is not following causality, and it may be somehow corrected. And there are modifications of perturbation theory, so-called analytic perturbation theory by Shirkov and collaborators. So this is also corresponds to so-called contour improved, right, perturbation. So maybe it's possible somehow to apply similar technique here.
We are actually working heavily with contours that are adapted, and we try to pin this down more thoroughly. On a side note, by the way, the corresponding analytic structure in QED is not complex conjugate poles, but actually is a singularity on the real axis.
It is Landau pole, right?
Which is the photon cloud, right? And this is precisely what you should get in QED. And that comes out in a Dyson-Schwinger calculation.
Yeah, I see. Okay,
yeah, thank you.
Frithjof, I had another small question. May I?
Okay.
I mean, going back to the discussion of this, in the first order transition. So, I mean, like in any mean field calculation, also like in NGL, can't I think in the first order region, this appearance of the second minima, and at some point that minima is favorable, what you say by physics choices it, I mean, I think calling it minimum pressure would be fine, I think.
This is usually what in mean field models you do, yes.
Yeah, and then I am little confused about the two boundaries, and the in between there was a line. Then I mean, shouldn't the system then? So basically, if we trace back,
I fully agree.
One is the restored minimum, one is the broken minimum. So basically, we are trying to trace back. So at some point, the system will go from the broken minimum to the restored minimum, and that's the
Absolutely.
point. You critical pion, what you say, right? This. So then, what are the other boundaries? So is it the appearance of those minimas, appearance and disappear, something like this, or
no? This is a misunderstanding. So you're fully right. Somewhere between these boundaries, the system goes from the broken to the symmetric phase. And this is dictated by pressure where this happens. However, we have not yet determined where this happens. So this mu Q critical pion is not the point where the first order phase transition happens. It's just the point where we do no longer find a solution in the corresponding Beatle-Salpeter equation for the pion. This is the point where we lose the solution for our bound state pion.
Oh, okay.
It's not the point of the phase transition.
Okay.
These points may coincide, I don't know, but without doing the calculation from thermodynamics, I just don't know. Yeah.
Oh, okay. I see. Okay. Thank you. Now it's clear. Thank you.
Yeah, sorry. Maybe the labeling is misleading you.
No. Thank you.
So I still have the raised hand by Nuxa here. Yeah, you opened your microphone, but somehow we don't hear you.
Maybe he could write the question in the chat.
Yeah, maybe you can write it in the chat.
Since I cannot see the chat now, you would have to
if there is something,
tell me the question.
Okay, so I think this somehow does not really work. So we are more or less coming to an end of our 1 hour session. At least I had still a question for Alexei. But if
we actually have a huge break afterwards, so if you do not mind, we have more time if needed.
Yeah, that's right. We can also continue for some time.
I would also have a question to the neutron star presentation.
Okay, so then maybe we switch first to the neutron star presentation and then can come back to whatever question is left over.
So maybe he can share his screen on page, I think it was 21.
Alexei, can you do that?
Yeah, I'm on it. No. There we go. Can you see it now?
Yes, exactly. It is this. I always have a little bit a problem when I see these curves because it gives the impression that one has two different equation of state when one enters from a hadronic to a quark equation of state. But when you're really doing taking one hadronic model and one quark model and doing a Gibbs construction or Maxwell construction, you have in principle 3 cases. You have first the hadronic equation of state, then a softening within the mixed phase region, and then a stiffening again in the quark phase region. Do you agree with this?
So what you're talking about is mixed phase construction.
Yeah, so the construction from the hadronic model to the really high density perturbative QCD. In between, you must construct the transition. And when you really construct it, then you have a softening and again a stiffening part as well. I think
if you have a microscopic model, of course, that is what you do. Here, we don't have a specific microscopic model. We don't know what makes these equations of states to do what they do. These are empirical bounds on the equations of states. There's lots of different equations of states in that cloud. I mean, that that wide band is made out of tens of thousands of equations of states, or hundreds of thousands of equations of states. Some of them have sharp first order transitions. Some of them have smooth crossovers. Some of them have behavior that resembles the mixed phase construction.
Yeah,
the specific microscopic model.
I know that. So I simply mean that it gives a little bit bad picture when you have the two straight lines there, because in principle in most of the models these are three different cases. So three different regions: the pure hadronic phase, the mixed phase region, and the pure quark phase region.
That's true if you look at it somehow in a very detailed level. I mean, and I should emphasize the blue line and the red line I just drew there. They are not fixed there. They're just to guide the eye. But the point there is that there, of course, can be all kinds of phase transitions within the hadronic phase. There can be all kinds of phase transitions in the quark matter phase. Like somebody in the chat mentioned something about onset of kaons. Sure, there can be kaons there, and you can have color flavor locking phases in the high density phase. However, what this plot here is showing, what is the overall, I mean, I'm asking much less refined question. I'm just trying to see what is the overall trend of the equation of state, and is that consistent with having hadronic matter or platonic matter. And sure, there can be all kinds of details how you go from one to another. I'm unfortunately blind to that because we don't have good enough data on neutron stars. And hopefully all kinds of detailed questions like this can be answered in the future.
So I'm stressing this point because I think when you look at possible signatures of a hadron quark phase transition, for example, in the neutron star merger, it's important that you, for example, before the merger, you would have low mass stars with no phase transition, but then when they merge, the density increases and it goes first to the part where the strong softening comes, and this shrinks the star and speeds up the rotation speed, and as a result, the emitted gravitational waves. But then later, when the pure quark phase comes, again something changes. So I found this important when discussing how we can detect the hadron quark phase transition with gravitational waves.
That's absolutely true. And under this wide band, there is all kinds of behaviors that can happen. And some of them can lead into a smoking gun type evidence like you were mentioning, but some of them don't.
Okay, thank you.
Alexei, can you actually open the chat? There are about 3 or 4 questions for you. Maybe you can have a look and try to answer them.
Can somebody who knows how to use Zoom tell me how I can keep the full screen?
On the baseline, when you go to the bottom of Zoom, there should be a bottom with...
Okay, thank you.
When you go to the end of the series of chats, there is a question by Natalia and a few more.
Okay, so have we used baryon number chemical potential, and what if we used quark number and strength? So this, I mean, the perturbative calculation is of course done with 3 quark number susceptibilities different from UD and S, and then what you do is you look at charge neutral beta equilibrated matter, and here, because the stars are assumed to be charge neutral in beta equilibrium, the astrophysical constraints of course come for beta equilibrated matter. But from the perturbative point of view, everything is done with generic quark number susceptibility, quark number chemical potentials. I hope that answers Natalia's question. And okay, so for the pion and kaon condensates, so as I mentioned, there can be all kinds of smaller phase transitions happening in this broad band that we draw. What we are asking is much less refined question than that. We are asking if the overall trend is that which is predicted by hadronic or atonic matter. And Matthias asked me his question already, and the last one is not for me.
Okay, thank you. Are there other questions for Alexei? I mean, I guess my question, the question I had, you mentioned several times the high temperature phase being conformal. Is that, I mean, in QCD calculations, one of course is more concerned about deviations from conformal behavior rather than having conformal behavior. So how important is that for you?
I mean, if you would have free massless quark-gluon plasma, then of course it would be conformal. And then in reality, it's only approximately conformal. But that is somehow the baseline to which we are comparing our expectation. And that's, for example, seeing why you and your colleagues plot P over T to the fourth. Is that at large temperature, it goes to the conformal limit where it's flat. And so that is the model to which you compare your data.
But in some sense, it's still far away from Stefan Boltzmann.
That is the number of degrees of freedom. Conformal just means that it's flat.
But if I may interject here, perhaps it also makes a difference whether it is a strongly interacting conformal or weakly interacting conformal. But because when we approach Stefan Boltzmann, we are talking about the free field, basically, so very weakly interacting theory, while we may have a near conformality, which is still strong interacting, or this does not, yeah.
That is true. I'm not making the point that we could use perturbation theory at densities around the kink. What I'm saying is that we have empirical reasons to believe that the equation of state looks like an extrapolation of the perturbative calculation to a regime where we don't have perturbative calculation under theoretical control.
Well, if I can, I have probably the question related to maybe also a small comment related to the previous two. Indeed, it looks like then in perturbative regime there is just near conformality, and you should not expect any kind of phase transition. And in order to have really phase transition, you need some dimension scale, which is like string tension, just or just some meshes. And so here, my question is to which extent are the mass parameters, which are the just order of lambda QCD, which is say strange quark mass, which was discussed here, how they're important. And comment is that, for example, in QCD at 0 temperature, sometimes it's possible to make a sort of matching, the perturbative expansion plus some analytic, some higher twist, and say some chiral perturbation theory expansions, and some sort of matching. Maybe here some kind of different expansions and matching can be also possible, or maybe this is what you are already doing?
Okay, so let me answer first your matching question. So one could do that, and that's something that we did 10 years ago. However, so you could take this perturbative result and extrapolate it here where you don't believe it. You could take these nuclear theory calculations and bring them up here where you don't believe it, and then make some kind of a Gibbs construction or Maxwell construction. But I don't see the point of extrapolating calculations to a regime where you don't believe them. And so what we do is more general. We say we don't know what happens here. We are not willing to extrapolate these calculations, but instead we will interpolate. So that is more conservative thing to do what you are suggesting. Of course, if you want a particular model which is based on microscopic assumptions, you could do what you are suggesting. However, if you want to keep, if you don't want to input any other theoretical assumptions, you don't want to do that, or I don't want to do that. And the other question was what mass scales there are in the calculation. There is a strange mass, and that is of course in these calculations. However, in the region where we trust the calculations, which is somewhere around here, that doesn't play quantitatively very significant role. And so basically, that's a small perturbation, and you can think of the calculation without this strange Quark mass. But then you say that you need the string scale to appear, and what I find somehow really remarkable is that if you see when does this equation of state somehow diverge, well, it diverges exactly at the not exactly, but roughly at the scale of neutron mass, and that's of course because then the running of the coupling shoots up, and that is the place where the scale enters into this game from the running of the coupling, and so even though this calculation knows nothing about confinement, it still knows how to fail at the confinement scale.
Does it, you mentioned the running, so does it mean that it is some signal of Landau pole of QCD?
Yeah.
In some sense, I was mentioning this. Somehow Landau pole, of course, it violates causality, and it's possible to somehow treat it in analytic way, imposing the analyticity. Maybe something like that can be also possible here.
I don't know, you will have to tell me. That would be very interesting.
Okay. Yeah, I think we had an interesting and long discussion.